This is lesson 3.1, functions. And today we're going to look at what is a function. You may or may not have heard of these before, but what we're going to do is go through the different properties of functions and exactly how they operate. But let's start with a couple of definitions first. And the first one is this definition of relation. And when we talk about a relation, we're talking about any time inputs are paired with outputs. For example, you're probably familiar with an ordered pair, right? You know, like an ordered pair XY. That actually represents a relation because the X represents the input and the Y represents the output. And so when we have an ordered pair, we're pairing an input with an output. And so that's probably the most common one that you'd be familiar with in terms of inputs and outputs as far as a relation goes. And today with functions, I want to introduce another notation to you. Sometimes instead of writing y, sometimes you'll see this notation. It's read f of x. And what this means is that it's a special kind of relation. It's this thing that we call a function that is going to hold certain properties, and we'll talk about those today. But this is, sometimes you'll even see this y equals f of x because we want to remind ourselves that if it's a function, that this notation f of x specifically refers to the output of that function. And so what is a function? Well, a function is a special kind of relation that pairs each input with exactly one output. In other words, we said that a relation is just the pairing of any input with any output. But a function says that if I take an input, there can only be one output that gets paired with it. So in this first example, we're going to determine whether or not each of these relations is a function and then explain why or why not. So if you look at part A, we have 5 different ordered pairs here. And again, remember that a function is a relation that pairs each input with exactly one output. So the first thing I want to do is I want to look at all of our inputs, which again in an ordered pair is going to be the first number. And what I notice right away is every input is different, which immediately tells me that this has to be a function because each input is paired with only one output. So yes, this is a function. If we look at B, however, in this case, notice that the very first ordered pair has a 1, the very last ordered pair has a 1. This technically isn't an issue, it's not a problem. Where the problem occurs is that the first one is paired with a 3, the second one is paired with a 5. And this can't happen in order to be a function, because a function is a relation that pairs each input with exactly one output. I have an input of 1 that's paired not with one output, but with 2 different outputs, 3 and 5. So this is not a function for that reason. All right, C, we have a slightly different representation now of a relation. But again, if you notice the top row is the X, the bottom row is the Y. And we could easily write these as ordered pairs. I could write this as an ordered pair 0, 0, or an ordered pair 2, 1, and so on and so forth. But again, as I look at the X's, I notice all of the X's are different. And immediately I know that this is going to be a function because again, each input is paired with a unique output. So yes, this is a function. And then finally in D, again, we have an issue here because we've got this input, right? These are the inputs in the first box. These are the outputs in the second box. And I notice that I've got an input 2 that goes to 2 different numbers. It goes to -4 and it goes to -6. In other words, if I think of this as an ordered pair, I would have 2 -4 and I would have 2 -6. I have one input that's going to 2 different outputs. That doesn't work for a function, so no, not a function. So that's how we can tell from just kind of the numbers. We always want to look at, for each unique input, for each number that we're using as an input, is it paired with a unique output, and only one unique output. In some of these examples, if you had that one output that goes to 2 different, or excuse me, one input that goes to two different outputs, it's not a function. Another way we can tell whether or not a relation is a function is by its graph. Because a graph is really just nothing more than a bunch of points that have a relation of x and y, right? We could take a point on a graph, and I'll show this over on the far right side here. I could put a point on this graph, and that point has an ordered pair xy. It might be 3, 5 or 2, 7. We don't know what the ordered pair is, but we know that it has some ordered pair xy. And so again, a graph is nothing more than a relation. And the way that we can tell if a graph represents a function is by doing what's called a vertical line test. And in the vertical line test, what we do is we simply draw vertical lines through the graph. And if that vertical line will only ever hit the graph once, then it's a function. But if I can find even one vertical line that hits the graph twice, it's no longer a function. So again, if you look at the examples that we've got here, in the first one you've got these set of points, and they've got a line already kind of drawn through, right? So that hits the graph, it only hits it in one spot. If I draw another vertical line, it only hits the graph once. And every vertical line I draw is only ever going to hit that graph one time, which is why this is a function. But if we look at the next graph, when we draw that vertical line through that graph, it hits the graph in two different places. So because it hit the graph twice, it's not a function. So that's how we can tell from the graph, is using what's called a vertical line test. So go ahead in number 2, and why don't you take a minute, pause the video, and try these on your own. See if you can figure out whether or not they're functions, and then you can start up the video to see my solutions. So for part A, this is a function, because again, there's no place where you can draw a vertical line twice through that graph. B, for the very same reason, is also a function. We've got these dots lined up in a horizontal row. Every single single vertical line I draw is only going to hit that graph once. In C, there are places where I can draw a vertical line and it only hits the graph once. But remember, I just need to find one vertical line that hits the graph more than once to make it not a function. And in this case, I can draw a vertical line here. It hits the graph 3 different times. This is not a function. And then finally in D, again, every single vertical line I draw is only ever going to hit that graph once. This is a function. There's one other thing I want to point out with these graphs. You'll notice that 3 of the graphs, A, C, and D, all have these nice smooth curves or lines. In other words, all the points are connected. But in B, you have individual dots that make up this graph. And we actually give names to these graphs based on what they look like in that regard. So in this case, we would say that A, C, and D are called continuous graphs. Continuous because when we go from point to point, they're all connected. It's a continuous or connected path through that graph. The other type is, for part B, we call this a discrete graph or a discrete function. And in this case, what you have are individual points that are not connected. And so we'll just say individual points not connected. In other words, if you want to really think of it another way, a continuous graph is one where I can put my pencil down and I can trace the entire graph or draw the entire graph without ever lifting my paper. In a discrete graph, I would have to take my pencil off the paper in order to go to the next point and the next point and so on and so forth. So just be aware that we have different names for these types of graphs, continuous and discrete. All right, well, let's move on to the next idea here. And that is this idea of domain and range. And these might be words that are familiar to you. When we talk about domain, we're talking about the set of all input values, or all possible input values. So the set of all possible input values. In other words, it's the set of all the, if you want to think of it this way, the x's, if you think in terms of x and y's. And then the range is the set of all possible output values. And again, if you want to think of it in terms of x and y, it would be your y values. So one of the things to note is that the domain, we sometimes call the x variable the independent variable because we typically will choose any random value for x and we'll plug it in. And then the range represents the y or the dependent variable because it depends on what we used from the domain. So the domain maps to the range. In other words, we pick a value from the domain and that value will determine then what value goes into the range. So let's kind of try to put that together in terms of some graphs here. So in number 3, it says identify the domain and range represented by the graph. So again, the domain is the input values, or in this case, it's going to be our x values, and the range is going to be the output values, or in this case, our y values. So if I look at these points, we have a point at -3, -2. This is at -3, -2. So its input is -3, its output is -2. In other words, -3 is part of the domain, -2 is part of the range. And in fact, it might help you to actually write the ordered pairs for each of these points. This is -1, 0. This would be at 1, 2. And this would be at 3, 4. Because now the first number listed, that x value in each of those ordered pairs, represents the entire domain. The second value, or the y value in each of those ordered pairs, represents the range. So the domain in this case is going to be -3, -1, 1, and 3. All of the x values are the first number in those ordered pairs. The range is the second number, -2, 0, 2, and 4. And again, to kind of go back to that idea of how the domain maps to the range or how the range depends on the domain, what we'd likely do in a situation like this is we would take -3, for example, we might plug that into a function, and that output would give us the -2. So the -2 comes from the fact that we plugged in or used the -3 from the domain. Well, again, I'd encourage you to try B and C. These might be a little trickier. We'll do B together, and then I'll have you try C. Because B now is a continuous function, and so how we write our domain and range is going to be a little bit different. You'll notice in A, we could write individual values because it was a discrete function. They were just all individual points. But in B now, it's not just integers, because between all those points are fractions and decimals and other numbers that we could use as part of our domain and range. So what we want to do here is when we talk about domain and range, we're going to talk about it as an inequality or set of values that we write as an inequality. So for example, in this case, our x values, so again, almost think of this graph as being bound between these two lines, and the x value on that first line on the left is -2, on the right is a +3. So we want to be very specific to only look at the x values when we're talking about domain. The x values that are being used are -2 to 3, and let me erase those lines so you can see. We've got closed circles on the ends, which means we're including those points. So our domain is -2, less than or equal to x, less than or equal to 3. In other words, it's all of the x values between -2 and 3, including -2 and 3. When we talk about range, again, we're talking about the y values, so now we want to do something similar, but in this case, we want to look specifically at what are the y values being used. So again, if I think about like the line at the bottom and top that kind of close it in vertically, it won't go any higher or any lower than those lines. That top line is at 2, that bottom line is at -1. That defines our range. It's the y value. So in this case, y is greater than or equal to -1, less than or equal to 2. All right, so again, if you want to try C, feel free to stop the video and see if you can write the domain and range for that. And then when you start it up, I'll go through the solution. Okay, so again, when we look at domain and range here, we want to be very careful about using the x's for domain, the y's for range. So when I look at the x values, this starts at 1 and it stops at 5 as I kind of go from left to right. And so my domain are values greater than or equal to 1, less than or equal to 5. So I'll say that 1 is less than or equal to x, is less than or equal to 5. And then likewise for range, when we talk about that, again, we're talking about the y values. So I want to look at how low and high the graph goes. In this case, the graph goes up to 4 and down to 0. So my range is y greater than or equal to 0, less than or equal to 4. All right. Well, I mentioned these words before, independent and dependent variables. And let's define those more clearly. So an independent variable, again, represents the input or the input values. We'll say it that way, represents input values. In other words, you can kind of think of it as your x values. And the output is the dependent variable. So the dependent variable represents output values, or more commonly thought of as the y values. And again, the idea is that it's called a dependent variable because it depends on the independent variable. X is independent. It can go off and do whatever it wants. It can be whatever it wants. And then whatever that is determines what the dependent variable is. Okay? So with that in mind, let's take a look at these last couple of examples then, number 4 and 5. Number 4 says the function c equals 6t plus 8 represents the cost c for t-shirts plus shipping. Identify the independent and dependent variables. If the domain is 1, 2, 3, 4, and 5, what is the range? Okay, so let's kind of break this down. So we've got this function where the cost c is based on 6 times t plus 8, where t is the number of t-shirts. And in this case, then 8 represents shipping. So if you really want to think about what this function is doing, it's basically saying it's $6 per t-shirt plus a flat rate of $8 for shipping. So it asks us then to identify the independent and dependent variables. And the question you want to ask yourself is what depends on what? I know it sounds a little funny, but that's going to help you kind of recognize which is the dependent and which is the independent. In other words, which is the variable that we might plug a number into, and then what variable depends on the number we've plugged in. Would it make more sense that we plug in the cost and from the cost determine the number of t-shirts? Or is it more likely that we plug in the number of t-shirts and based on that get a cost? Well, if you said the second, you're right. The t is our independent variable because we plug in the number of t-shirts and then based on the number of t-shirts we get a total cost for this order. So t is our independent variable and c is our dependent variable. So independent variable is t, and c is our dependent variable. Because c depends on t. The cost depends on how many t-shirts we buy. Now the second thing it says is that if the domain, remember domain is our x values, is 1, 2, 3, 4, and 5, what is the range? Well, basically what that's asking us to do then is actually plug in those values and figure out the range. So if I plugged 1 into that function, I'll just do this as an example. If I take 1 and plug it in into t, I get 14. If I plug in 2, I get 12. 6 times 2 is 12, plus 8 is 20. And so on and so forth. And if we keep plugging in the other numbers, and I'll let you do this to verify that, if you want to plug in those other values, we get 14, 20, 3 would give us 26, 4 would give us 32, and 5 would give us 38. Do you notice that those numbers just go up by 6? Because the shipping was a flat rate of 8, so that doesn't change, but every time we add a t-shirt, the cost is going to go up by 6. Another way that we could have represented this was with a table. So we could have said that T is 1, 2, 3, 4, 5, and then C is 14, 20, 26, 32, and 38. Recognizing that, again, T is our domain, and C is our range. All right, last example here, number 5, says the function T equals 19m plus 65, which represents the temperature T in degrees Fahrenheit of an oven after preheating for m minutes. Identify the independent and dependent variables. And then it says a recipe calls for an oven temperature of 350 degrees. Describe the domain and range of the function. Okay, so let's kind of again break this function down a little bit and then answer those questions. So we've got this function, again, T is the temperature, M is the number of minutes that the oven has been preheating. So obviously the longer the oven has been preheating, the higher the temperature. We're going to take 19 times M and add 65 to it. All of that makes for a higher temperature. So again, ask yourself the question, what depends on what? Well, in this case, the temperature depends on the number of minutes, correct? We start to preheat the oven. After a certain number of minutes, we check the temperature. So M is our independent variable, and T is our dependent variable. M is independent, T is dependent. So again, if you think about the domain and range, actually, first of all, it says a recipe calls for an oven temperature of 350. It really doesn't say any more than that, but I think what we want to do is just use that to figure out how long it would take to preheat to 350, just to have an example. So if I take the function, if T is 350 degrees, and I set that equal to 19m plus 65, if I subtract 65 from both sides, I get 285 equals 19m. And then dividing by 19, I'll write it over here, m equals 15. What that means is that at 15 minutes, the temperature will be 350 degrees. Okay, so at 15 minutes, because again, m is minutes, so at 15 minutes, the temperature will be 350 degrees. So that's just an example of what this equation is doing, where we could plug in minutes to get temperature, or in this case, we knew the temperature, we could figure out how long it's going to take to reach that temperature. Now let's talk about domain and range. So for the domain, notice that we don't have really any helpful information. It didn't actually tell us what to use for the domain, but let's think about what might make sense for this one. Would it make sense to go less than 0 for time? Probably not, because somehow we'd be going back into the past. So I think the smallest time we'd want to use is 0, which kind of represents the resting temperature of the oven when it hasn't been turned on yet. So we could use 0 as a low point. And the high point kind of depends on the oven, right? It kind of depends on, does the oven able to go up to 400 degrees? Is it able to go up to 500 degrees? But I think for just purposes of example, and because we have a kind of a high example already, we've got this example that in 15 minutes, the temperature will be 350 degrees. Why don't we just use that for our example for the domain? So let's suppose this oven was only able to go up to 350 degrees. Well, we know that it takes 15 minutes to get there. So our highest number of minutes is going to be 15, because at that point, the oven would have reached its highest temperature of 350 degrees. The range, again, is the output. And there's a couple ways to think about this. One is as I talked about earlier, 65 degrees is kind of the resting temperature of the oven. It's the lowest temperature it's going to reach. But the reason I know that specifically is because the smallest number in my domain is 0. And if I plug 0 into that equation, 19 times 0 is 0, plus 65 gives me 65. That's going to be my lowest value in my range. And in this case, we're talking T for temperature. And the highest value, well, we said 15 minutes was our highest time, and that relates to the highest temperature of 350 degrees. So our range would be between 65 and 350 degrees. The difference between 4 and 5 is that number 4 was a discrete function. Again, there's that word again, discrete, meaning that it's not connected. I would buy 1 t-shirt, I could buy 2 t-shirts, I could buy 3 t-shirts, but it wouldn't make sense to buy 2.5 t-shirts. So it's discrete, we've got these individual points. Whereas number 5 is continuous because we can have different times in between minutes. It doesn't have to be exactly 14 minutes or 15 minutes. Maybe I preheat the oven for 14.5 minutes or 14.25 minutes. And so it's continuous because all those points are connected. We could use any point in between two other points. And that's why you also see a difference in how we think about range and domain. In number 4, the domain was a specific set of numbers, 1, 2, 3, 4, and 5, and the range was a corresponding set of numbers, 14, 20, 26, 32, and 38. Whereas in 5, because it's continuous, we had to write our domain and range as inequalities. Well, that completes this lesson. I hope that made sense to you. I hope it was helpful. Make sure you do the homework that corresponds to this. Contact your teachers with any help that you need.